about a minute and a half. So this is going to be the last stretch of activity today. I have had 2 hours and a half of meetings this afternoon. Kind of interesting stuff. We actually got a rep from Honor Lock. That's it. A rep from Honor Lock, which is another type of proctoring service comparable to Proctorial, to give a demonstration on Zoom. So that was a little interesting. I was interested in the mechanisms and the technology that they use in the back end. Yeah, well, the proctoring service is still required because a lot of classes are online only. Like this class, CISP310, I think at CRC it has always been 100% online. So, and then there are many other departments, who prefer to teach their classes online. So, so proctoring services is actually needed even after COVID-19. I mean, I'll be going back to face to face. I mean, I pretty much prefer to teach the class in a face to face fashion. But there are those who would like to continue to teach online, or they have been teaching online all along. And there are some people who believe proctoring helps. So that's the other part. I mean, I just came up with a little part list myself, to basically defeat most of these proctoring services. And it doesn't need to use, virtual machines, doesn't need to use all kinds of stuff. Well, I suppose there's a little bit high tech stuff in it, but it's totally defeatable. I mean, so yeah, the district has to, we used to have a subscription to Proctorial because of the state chancellor's office, but we have been paying for our own. The district has been paying for its own subscription to Proctorial for about 6 months, and now we are evaluating other options. So that's what some of the meeting in the afternoon was about. All right. Well, it is 31, so I'm gonna get started. All right. So Aaron has it right. Okay, we're gonna talk about Struct today. So we're gonna talk about how to use structures and some of the stuff that is kind of interesting about structures. So that's kind of the focus of today's class. And what I'm gonna do is I will first take a look. Yeah. So we'll go ahead and first take a look at a C program. Let me see if online GDB is here. Yep. In fact, I have two tabs of online GDB. So I'm gonna open up this one. Alright, so this is from my other class about permutations. So let me get rid of this, okay, and then we'll start with what is relevant for this class, okay? Yeah, 440. It's kind of a fun class. I mean, it's a different kind of class. I'll put it that way. Alright, so we're going to talk about struct, and we'll start with something relatively simple. Okay, so we'll say, okay, here's a struct, and I'll call this, uppercase C for complex. Oh, okay, great. Now, online GDB does all kinds of automatic, typing, so I have to be careful what I'm typing here. Math without a math type part. Yeah, sort of. I mean, if you think about it, the entire computer science field is really a subfield of math. So when you get into computer science, you're already getting into math basically. Nope, computer science particularly is a subfield of math. Um, because it's invented. You cannot call a science a field of math, because math is the language in order to describe what scientists have discovered about nature. But computer science is not science. in fact, most of the time when you hear the word science, it is not science. So computer science is not science. Cognitive science is cognition. Cognitive science? Yeah, cognitive science is not science. Political science is not science. Yeah. Oh, okay. All right. Thank you. I'll go ahead and do that. I'm just hacking along here to get this program to write this program. All right, so we have struct C, and inside here it's kind of like a class, okay? Because you have taken CISP360, so I'm suspecting you know something about either class or struct, okay, depending who's teaching that class. So struct is like class, except everything is public by default, and that's in the context of C++. But I'm in the context of just regular C, so that means it's you cannot have member functions, you can only have member properties in this case. All right, so we're gonna have int 8 int u int 8 underscore t. So this is an unsigned 8-bit integer. We'll call this I, and then we'll have u int 8 underscore t j. Okay, and they don't have to be unsigned. They can be signed. It doesn't really matter in this case. So we'll just make them signed. Now this is the minor difference that you kind of have to pay attention to. Is if you are using regular C and you're defining a struct, at the end of the structure definition, you need a semicolon. This semicolon is not needed in the case of C++ when you're defining a class. So this is a minor difference between the two languages, C versus C++, and this needs to be here when you're using regular C. And then we can define a function, right? It means we can define a function, say int 8 underscore t, and all it does is to return the member I. Okay, so we'll say get I from a pointer that is pointing to a struct C. There we go. And as you might expect, the only thing we need to do is to say, let's dereference, p as a pointer. And once p dereferences, it becomes a struct C, and then we can say which member we want to access. And in this case, we want to access member I. That's what we are returning. And we are not going to talk about bit packing, just because it's it is part of the language, but how it is implemented is very dependent on the compiler. So we are not going to talk about bit packing in this case. All right, so we got main, and then in main we have a local variable that is a struct C. So now we have a struct C. We call this var for variable, and then we have another variable which is an int 8 underscore t. We'll call this x, and all we want to do is to say x equals to get I, and get I requires the address of a struct C. In this case, the var is a variable of the type struct C, so we're going to take the address of var in this case, and that's the end of the program. Does C support that for pointer? Yes, it does. In other words, what Omar is referring to is on this line, I could have used this syntax as instead. So this is also P and then the little pointer to the right hand side, and then I means exactly the same thing as the way that I have typed here. So you can kind of look at this thing here using the pointer thingy as a shorthand of doing it the other way. But the other way is actually more clear. I think it quote unquote makes more sense because we are just combining dereference with a membership operator, as opposed to using the pointer thingy, which looks completely different compared to using a dot to access a member, but it really is just a special case where we are starting with a pointer instead of starting with a structure to begin with. So that is the only difference. Because this is regular C. That's all. Because in regular C, you cannot say cvar in this case. You have to say struct cvar in regular C. In C++, if C is a class, then you just say C var. So minor syntax differences between C and C++. Yes, you can use typedef, but personally, I don't use typedef, just because, it doesn't hide that much stuff, especially in this case, so there's no need to use it. No, it would not be class C var, because if it were a class, you would have been using C++, in which case you don't spell out the word class when you are defining a variable. All right, so let me just illustrate one more thing. Is right here, I'm just going to initialize, member I or var with something. Okay, we'll just initialize it to what, 15. Okay, just a random number. There we go. All right, so now we look at this code, and I hope in regular C we don't have any questions, but I'm gonna let you guys ask. If you have any questions about this program, go ahead and ask that question, because otherwise I would assume that you know enough about pointers and structures so that you know what this program is supposed to do. Well, the way C++ started out is really quite interesting. I actually met the guy who invented C++, Struct, once, at a conference, and he was explaining, why C++ still has a lot of, the kind of icky, stuff in C, kind of like, why can we use a pointer as if why can we use a pointer as if it is an array, and why an array doesn't know its length, that sort of stuff. And he said, he had to keep it backward compatible, because nobody would be using C++ if it wasn't backward compatible. So it was a kind of interesting discussion. Because at the time, I think Java was available already, so it was a contention between C++ and Java. And the guy said, well, if he did not make C++ backward compatible mostly to C, then people would not have used it. Yeah, C sharp, I think, is genuinely a mistake on some executive working for Microsoft. So somebody probably wrote is plus plus overlapping just a little bit, and then the executive looked at that and go like, that looks like sharp. Yeah, I like that name. C sharp sounds pretty sharp to me. It sounds really smart. Let's just use C sharp. Yeah, so I think I think it was a mistake. And then later on, they couldn't change the name anymore. They could not admit that they were just looking at the overlapping plus, the two pluses, they were overlapping, and say, oh, yeah, I think we made a mistake. We thought that it was a sharp symbol, but it was actually two pluses, kind of overlapping a little bit. Bad penmanship. Yep. Yeah, C sharp is compiled. And the what Microsoft, typically did, and probably still does in industry, is they would poison a programming language. So they don't just flat out, get rid of the programming language. They would poison it. They would use some parts of it. They would change some other parts of it, so that it is not quite the original thing, and it becomes a Microsoft specific thing. That's typically what they do. I mean, they have done it several times already, so I wouldn't be surprised. All right, so at this point, we're gonna take a look at this program, and we'll put a breakpoint on line 20 just to make sure the program works, just to make sure that it compiles and it runs the way that we think it should run. So now we go to debug, and of course I missed something. It's on line 22. I forgot a semicolon. Yes, somebody's gonna type, yep, again. Yep, it is. There we go. Alright, so now we just hit run, and to get to this point. Okay, so when it gets to this point, there are a few things I want to illustrate already. Okay, because I want to show you the addresses. Okay, the addresses of things in this case. So we're gonna say, where is var? Okay, So this is where var is. It ends with an address of EE. Then we ask, where is member I of var? Member I of var is at exactly the same location. Are you surprised? I mean, are you surprised that member I of var, which is of type struct C, is actually at the very beginning of var itself? I mean, that is hardly surprising, because it is the first member of a struct C. So as the first member of a struct, that member having the beginning, the starting point, in terms of memory, as the structure's own beginning, that is not surprising. So now we want to say, what about J? So we say as ampersand var dot J, and it is just one byte after. See how one ends with an E and the other one ends with an F. So that kind of makes sense too, because if the compiler, I mean, it doesn't have to be like this. If the compiler says, I would like to put J first and then I, it would not be wrong. Okay, the programming language does not define that the addresses of the members inside a struct have to follow, the addresses have to follow that order. So there's no requirement for J to be later or after I. That is entirely okay. But it just doesn't make a whole lot of sense, because from the compiler's perspective, it would have parsed the definition of the member I first and then the member J. So it kind of makes sense that from the compiler's perspective, that it would assign an offset of 0 to member I and then an offset of 1 to member J. So in this case, the fact that J is only one byte after I kind of depends on how you set up the compiler too. So even with the same compiler, there are switches that you can use in order to tell the compiler, no, I want to optimize for speed, or I want to optimize for the number of bytes and so on. So it can still vary. Okay, how, where it puts the member inside the structure can still vary, depending on the switches that you supply when you compile a program. Yep, yep. That's part of it. Pound define Mac versus pound define Win, is part of it. Windows is interesting because when we look at Windows, the core part of Engine, or the core part of Windows, I think at some point, okay, they used the Pascal standard instead of using the C standard to pass arguments. So that kind of makes a mess, okay, out of things. But at this point, we're just focusing on ampersand var. So right now, if we say, what is member I of var, it says it's 15. Makes perfect sense, because on line 19, we did initialize it, right? So if I continue execution, if I single step, we'll be single stepping into the get I subroutine. So from the subroutine's perspective, and I ask, what is parameter p? And it says parameter p is a pointer pointing to this location. And that makes perfect sense too, because that is exactly where var is supposed to be. So we are just passing the address of var to get I, and then inside get I, we first dereference p, which theoretically speaking gets us back the entire structure, and then we say, oh, by the way, we just need one member of the entire structure, member I, and that's what is supposed to be returning. So when we single step again, it goes back to main, and one more time. So now it goes back to main, and x should be 15, because after all, we are really just returning the value of member I of the structure that is pointed to by the address of var. Yes, that's a lot of stuff to say just to say the member I of var. So we'll go ahead and print x just to make sure it's 15, and that's kind of the very predictable outcome of this program. So the program is really predictable, but the whole point is, how do we do this in assembly language? That is our focus today. So we'll look at this program, and we'll go ahead and do it in assembly language, in TTP ASM to be specific. This type of program is probably more compact. The program code is going to be, it will contain fewer instructions. if you were to do that using the x86 instruction set, because there are certain addressing modes of the x86 instruction set that can basically combine a few TTP ASM instructions into one single one. And that's also why the x86 is known as a CISC processor. CISC, CISC, stands for Complex Instruction Set Computer, as opposed to the TTP, which is more of a RISC design. It is not a pure RISC design, by the way, because there are certain instructions that I could have eliminated, and we'll still be able to write code, to do everything that we need to do. But the code will be so tedious that it's not even funny. Even I would have a problem with that. So that's why I made the TTP not completely RISC. It's not a pure RISC type processor, but it's close. Yeah, the increment instruction, interestingly, is not one of those, because I did want the increment instruction not to change the flags register. It has to do with the JMPI, the JCI, the JSI. All of those J blah blah I instruction are not really necessary, because I can load the immediate into a register and then use a JMP and then the register. But that is just insanely tedious. Okay, and I first Okay, the first revision of the processor was like that, and then even I look at my code and go like, no, this is counterproductive, and that's why I have the JMPI instruction where it combines. It doesn't need an extra um, uh, LDI instruction to load something into a register and then use that register to specify where I'm jumping to. Not necessarily. Most of the processors that we call RISC processors, and that includes the AVR of Arduino fame, and also the ARM processor of a lot of fames, right? Because that's used in the Raspberry Pi, it's used in almost all of the mobile devices and so on. So even all of those so-called RISC processors, they're not pure. Okay, in other words, the designer of those processors look at what compilers need to do and what kind of code the compiler needs to compile to, and they just make certain decisions and go like, well, these instructions are kind of CISC type instructions. Even in other words, we could have um, they're not necessary. Okay, we could have used smaller steps to implement exactly the same thing, but because it is used so much, because the compiler cranks out, that kind of code, and they just decided, hey, it's just a whole lot more efficient, if those are actual instructions. And that's why the so-called RISC processors are not pure in the sense that the instruction set is every single one instruction of the instruction set is 100% necessary, but they are good ideas. Okay, they're practical to be included in the instruction set. So that's kind of the deal. Now, if you want a real CISC processor, you can look up the IBM Z Architecture. Now that's a whole different scale when it comes to CISC processor. Okay, if you think the x86 CISC processor has a lot of instructions, a lot of opcodes, wait until you see the IBM Z15 core. I mean, that's like a whole different scale of CISC. Anyway, getting back to here, and now our task is to implement this in assembly. So let me go pick up a terminal, and I have to pick the one that has the right size, and this one looks good. Okay, so we'll take a look at this one, and we'll look at the C code on the left hand side, and then the assembly code, the assembly code on the right hand side. And I have to be careful where my face is too, so I'm still covering a little bit of it. Okay, there we go. Alright, so that looks good. Let's go ahead and take a look at the assembly code implementation of this. So I'm just going to call this one struct.ttpsm because it's just illustrating how to use structs. Alright, so the first thing that we're encountering, the first question that we're encountering is, how do we represent a structure definition? Like, in the C code from line 3 all the way to line 7, how is that represented in assembly language? So I'm going to type it first, and then I'll explain, why it looks like that. Okay. So we'll start with a label like C underscore I. We'll define it to be 0. And then we have C underscore J, which is C underscore I 1 plus. And then we have C underscore size, which is C underscore J 1 plus. All right. So these three are basically label definitions. In other words, for the assembler, they are no different from any other label definition. The assembler does not understand that these labels are related to a struct definition, because a label is just a label. To the assembler, it is really just a symbolic name that has an integer value associated with it. And that's all the assembler understands. So it is us, that would basically look at these and go like, oh, okay. So with the first one, because I'm using the name of the structure as the prefix, and I'm using the name of the member in the structure as the postfix. So this way I'm combining those two into a label to basically mean, oh, this is the offset of member I from the beginning of a structure in a struct C. So that's what the 0 is. Okay, it's basically saying, if I need to access member I of a struct C, it is right at the beginning of the structure itself. So the next one is really just one step after the member I, which is member J. So I look at the offset to get to member I, and I just say, okay, just add 1 to it. Why are we adding 1? It's because member I only takes up 1 byte. And I typically would also define C underscore size. Not that size is a member, but I want to know how many bytes a struct C is going to take. So that is for that purpose, because if I need to allocate space, I need to know how much space I need to allocate when there is a local variable of struct C type. So that's what C underscore size is about. That's the purpose of this label. How is it defined? Well, it is defined as the last member, or the offset to the last member of a structure, and then the size of that particular member plus the offset. So that becomes the size of the structure itself. And some people is going to say, well, can't you just define C underscore J as 1 and then C underscore size as 2? Well, the answer is yes. But that would make it very brittle, which means if I decide to change and add another member, then I'm going to have to change a lot of things. But to do it in this way, which is a relative way of defining the labels, if I just want to insert something, I might need to change just 1 or 2 lines, and that would be the end of it. So that's kind of the reason why I define the labels the way they are now defined. Alright, so this is how I define the structure, and now we can get to the usual stuff. Okay, we have no op and then JMPI to main. And then we need to define the subroutine get I. So get I is going to, so the first thing we want to do is to look at what is on the stack. So we have parameter P on the stack, and then we have the return address on the stack. There are no local variables, but just using the standard that I have been using in this class, I'm still going to say that get I underscore local var size is 0. There are no local variables as it is right now. So this way I can use the template, which is LDIB local, name of the subroutine first, get I underscore local var size. We subtract that much from the stack pointer to allocate for the local variables, which in this case doesn't do a single thing because we don't have any local variables. And then we'll do about the same thing, except we are adding instead in order to deallocate the local variables, which obviously is not going to do a single thing because we don't have any local variables in this case. And then we have the usual stuff, which is LDBD, increment D, JMPB, as the 3 instructions to go back to the caller. So this is what I'm talking about, okay? Because these 3 instructions are used so often, when we get to the end of a subroutine, most RISC processors would actually have an instruction called return to do exactly the same thing. but using only one single opcode. And I decided not to use a return instruction in TTP because in this class, we are more concerned about how something is done, in terms of low-level operations, like, what are we doing to the stack pointer? What are we putting onto the stack? What are we reading from the stack, and so on. So I want to make that very, very obvious of what we are doing on the stack, and that's why I do not want to implement the instructions called call, okay, to get to a subroutine, and return, which goes back to the caller. I don't want to use single instructions for those because I want to expose the lower level operations, to the registers and also to the memory content in the stack. All right, so in between, now we can specify what this thing is trying to do. All right, so it looks like, it looks kind of complicated, but let's do it one step at a time, okay? Where do we start? We have to start with P, okay? P, the parameter. So now we have to say, okay, we need to get to the value of P because after all, we need to dereference P to get to the structure. So we need to get to P first. So at this point, I think most of you are at least familiar with this sequence. And I'm hoping that you guys can also explain why these two instructions together will compute the address of P and put it into register A. And we don't really want to know the address of P. We want to know what P is and what it is pointing to. So the first thing we do is to use a LDAA so that now A is the value of P. But even that is not what we want because we want to access a particular member of the structure that P is pointing to, and register A is now P. So register A is pointing to a structure, and we want to access the field or the member called I. So this is where we have to use C_I, which is defining the offset to member I from the beginning of a struct C. So we put it into a different register. I cannot overwrite register A at this point because it is containing something that's useful to me. So I have to use register B, and then we specify C_I, and then we add those two. So we add B to A. Now, which way you want to add doesn't really matter because either way we have to do one more dereference. So so now we have to do one more dereference of LDAA, and now register A has the value of member I of the structure that P is pointing to. Whew, that was a long sentence, but that's the correct description of what it is. All right, so I'm looking at the text channel and I do not, oh, there we go. Now we have questions. Are we going to initialize P? Well, P is a parameter. It is not up to the subroutine to initialize it. The caller from main has to do something, but I haven't written the code for main yet. So that's that question. That's the answer to the question of are we going to initialize P? The answer is no, because it is a parameter of a subroutine, so the subroutine itself is not going to initialize it. That defeats the whole purpose of having a parameter. Oh, okay, I see. Okay, so it's not initialization, but it is the definition of P. That is correct. Okay, thank you. So we do need to define P, but before we define P, I suppose we can do that. We can just do that. So it's P, and it is get I local var size 1 plus, and that's going to be P. Because P is a parameter, and get I local var size tells us how many bytes we have been using on the stack for local variables. And then the 1 plus here is needed because the return address is right between the local variables and the parameters. So that's why we have a 1 plus to basically skip the return address. So now we have the offset to P defined. Thank you. Okay, so that's what the text meant when someone said to initialize. It is the definition, not to initialize. Now, it is a very important distinction, okay? Because with labels, we are defining. There's no we are not initializing labels. Why are we not initializing labels? Because labels, once they get a value, it cannot change. Initialization, suggests that you are putting an initial value into something, and then later on that can change. But label definitions cannot change. So with labels, which is a static compile time slash assemble time kind of construct, we define. With variables and registers, we initialize because those can change over time as we execute the code at runtime. So there's a kind of important distinction between the two. And once again, with this code, I intentionally did not comment so that so that you can download this code later on, or you can just kind of type on the side, and then you can comment the code yourself. Because as you comment this code, as you track down what is in a register after an instruction, you will start to you will get a better understanding of how we access a member of a structure that is pointed to by a parameter in this case. Alright, so now we get to main. So main is not exactly a real subroutine. So we do want to emphasize that, regardless, we probably should initialize the stack pointer, and this is how we initialize the stack pointer to quote unquote 0. And then we have to look at the local variables of main, and it has 2. But what if our interpretation of it is wrong? Okay, what is it referring to? Okay, it looks like I skipped a few text messages. All right. Okay, so let me just go back to the point of the LDI. So these two instructions really don't do anything useful because get I underscore local var size is a 0, and same with these two. But I'm doing this as a template just in case there are in fact local variables. Then the code to allocate the local variables is already in place at the right place. Okay, so it's just good practice to do it for this class because we need to know exactly where to allocate for the local variables and where to deallocate the local variables if there are some. Now, if you just say, but we don't have any, well, then just define the local var size to be 0. Then it doesn't do a single thing other than to serve as a reminder that this is where we're supposed to allocate, this is where we're supposed to deallocate. It doesn't hurt except, it chews up like, a few more bytes in terms of the program code and takes a little bit more time. But as far as learning is concerned, I think at this point it is important to understand, how we allocate and how we deallocate local variables. All right, so next one is, but what if our interpretation is wrong? Commenting the wrong process. Well, you have to go with the trace too. Okay, so you kind of have to cross-check your understanding with what the trace is telling you, because if the trace says, okay, well, you think that you're loading the address of this thing into register blah, but the trace tells you it's otherwise, well, that means your interpretation is wrong and you need to go back and change it. But I already said it in class too. I actually verbally said everything that should be commented. So, it's already in the video being recorded. Let me just make sure it is getting recorded. So it's already in here. It's just that I didn't type it into the program itself. I'm banking on no one in class has a photographic memory when it comes to remembering just audioly, what I said, because otherwise, this wouldn't be an exercise. There we go. Can I turn on line numbers? Yes, I can indeed. Oops. Okay, not here. There we go. Alrighty. Yeah, try to trick you guys into studying. Yep. That's what all evil professors do. All right, so now we're in main. Now main does have local variables, right? So the way we define the local variables is, the first one we encounter on line 16 is going to be the one we first allocate for, or we first, how should I put it? That would be at location 0. That would be closest to where the stack pointer points to. That's the best way to put it. And then on line 17, that's the other one, which is going to be further away from where the stack pointer points to. So when we define the labels, it's going to reflect that. So var is going to be defined as label 0 to have a value of 0 because it is the first one that we encounter. And then we have x, and x is going to be defined as var 1 plus. Oh, wait, hold on a second here. Why are we using 1 in this case? That's not right, because var is not something that only has 1 byte, right? Because we are supposed to reserve enough bytes so that we can fit an entire struct C in here before we get to the location corresponding to local variable x. So this one is in fact incorrect. It is the size of C, so it's going to be C underscore size and then a plus. Okay, and now we can finish this up with using main local var size being defined as x, and then whatever number of bytes x is going to take, which is just 1 in this case, plus. So this way we know exactly how many bytes we need to reserve for local variables. And now we can do the allocation and then also do the deallocation. I always do those two at the same time. So we have LDIB with main underscore local var size, subtract b from d, and then we'll do the deallocation, which is just changing the add to the subtract to an add, and then we get to the halt instruction. So hopefully by the time we get to the halt instruction, the stack is balanced, which means we remember to deallocate everything that we allocated during the execution of the program. All right. So Zoe is correct. C underscore size is really just 2. Now, I could have just used 2 over here, but that would not be a very good idea, because if I decide to change the size of the structure just to add a few more members, then I have to go to everywhere where I just use the literal number 2, and then some of the literal number 2 may not be referring to C size, so now I have to analyze my program. But by using the label, I don't have to do a single thing. On line 31, I just have to change the way C underscore size is defined if I want to change struct C. The add one over here, that has to do with x takes up 1 byte. That's what the 1 is for. All right. Why not make var the size of C size? I'm not sure what you mean by that, because var as a label refers to the offset to the beginning of the structure, and then C size will tell us how many bytes it needs after the offset. Okay. Yeah, C size is 2, not 2 bytes. It's just 2. It's just a number. It's just an integer. So C size is really just 2. All right. All right. Oh, bless you. Okay. All right. It was never defined to be 2. This is how it was defined up here on line 3. That's how size is defined. But it boils down to 2. Okay, eventually it boils down to 2. So main underscore local var size is 3. That is correct. Yep. Okay. So I'm just gonna continue to write the code here. Okay. So the first thing we need to do is to put 15 into Yes. Okay. So I was just checking to make sure that I did the allocation. So I did. And so now on line 37, the stack is properly prepared so that we have the space for the local variables reserved. Okay. So it's very important not to refer to the local variables before the space is reserved. So that's kind of important. All right, so on line 19 of the C code, on one side we just have 15, so we can deal with 15 pretty easily, so I'm not too worried about it. And I would like to focus on the left-hand side first, okay? How do we compute the address of member I of local variable var? Well, don't you think we need to get to the address of var first, and then from there, try to figure out where I is within that region of memory? So that means, the typical thing that we do, which is LDIA with whatever we need to access, which is just the offset at this point. And then we say add AD to get to the address of var. Okay, so at this point, A has the address of var. And we know that var is a structure. And now we have the address at the very beginning of the structure in register A. But we also know we have a label called C_I that will tell us how many bytes do we need to go from the beginning of a structure of type, from the beginning of a struct C to the member I that we want to access. That's just C_I. So at this point we can say, we can just add that to A. So we can just say add A with C_I. And then we look at this and go like, darn it, the editor says this is not valid. We go like, why is it not valid? Right. Okay. So when we use add, you can only add a register to another register. You cannot add an immediate value to another register. That mode of operation simply does not exist. You go like, man, that's kind of stinks, right? So now we're going to have to do something like this. Okay, so we have to put it into another register like this, and then we add register B to A. Okay, so if this is a solution that you're giving me in the exam, I'm going to say, yep, that works. You get all the points. Not a problem. All right, so I'm just catching up on the text channel. So LDB, yep, so Darvish is correct. And then Luke said var:0 is the offset of the last byte in var. No, that's the beginning. That's the var:0 on line 30 is defining the offset of var from where the stack pointer is pointing to. So on line 30, we don't even need to know what is the type of var. We just say, hey, this is the first local variables that we encounter, and this is the closest to where the stack pointer is pointing to. That's why it is defined to be 0. I literally just typed it. Not sure what I just typed. Oh, okay, when you said, when you gave me the solution of LDBCI and then add AB. Okay, yes, that is true. All right, so we look at this and go like, well, that's gonna work, but that seems really tedious, right? Because we put a constant into register A, we add the stack pointer to register A, and then we put another constant into register B, and then we add register B to register A. That just seems kind of redundant. Well, the answer is true. Okay, you're absolutely right if you think this is sort of redundant, because we could have folded the addition of the two constants into one. So we could have done it this way. Looks clean, right? Because it is okay to put the addition of all the constants together into the expression that specifies the immediate value to put into a register, because those are all computable at assemble time. None of the var or C_I depends on runtime value, so they can all be folded, at assemble time into one single expression. The only thing that depends on runtime is the value of the stack pointer. which is register D. So that one cannot be folded into the same thing. It needs its own line. All right, so now what do we do? This is the address. Okay, so by the time we are done with line 38, we have the address of member I of the C structure that we call var as a local variable of main. What are we going to do with the address? Absolutely nothing yet, okay, because we need to load B with 15, which is the right hand side of the assignment. Now we can use A because A is telling me where I'm supposed to store the 15. So that will accomplish the C statement on line 19. So now we move on to line 20. So some people may be thinking, oh man, we have to compute the address of a structure. Computing the address of an integer is already tricky enough. Now we have to compute the address of a structure. But why would that make any difference? It's the address of something, and that something is a local variable. So we use exactly the same mechanism to do that. In fact, we had something that looks like that originally, but we'll put it over here. So now we load A with the offset from where the stack pointer points to var, and then we use add AD so that A is now the address of the local variable var. Oh, you mean this is it? You mean this is what we're going to push on the stack, when we are trying to push the address of var on the stack? Yeah, that's it. We are not pushing 2 bytes on the stack. We're just pushing 1 byte. We're just pushing the address of the structure on the stack. We're not copying the whole structure on the stack. We're just pushing the address to var on the stack. That's all we're going to push. Okay, so that means now we have to decrement D, reserve that space on the stack, and then store to that place the value of register A, which is the address of var. So now we got the argument pushed on the stack. Now it's time to call. So now we have LDIA with .6 plus, and then we have the usual, okay, decrement D, ST, DA, and then JMPI to the subroutine, which is get I. And then when we get back, we better remember to increment D because otherwise we have that argument sitting on the stack, and everything is off by 1 if we did not do the increment D. So we have to remember to do the increment D. So now everything is good. The right hand side is now computed in register A. Alright, so we got some traffic in the text channel. Is this why struct needs to be defined before main if they are going to be accessed in main? That's a C thing, okay? The C compiler is just kind of picky about, if you don't tell me what a struct is, I can't, I don't know, I wouldn't know how to allocate for it. So that's kind of a C thing. The compiler could have gotten around this problem just by using a little stub and go like, okay, we'll assume the structure is going to be defined somewhere, and I'm just going to put a placeholder here, so that when we finally know what is a struct C, we can come back here and fix it up. It could have done that way, but I think C is a very, at least at the very beginning, C was a very simple programming language where the two authors of C really did not want to write a compiler. Okay, what did they want to do? I'm gonna let you guys think about that as I finish the program. So the question is, what did the authors of the C programming language wanted to do when they invented the C programming language? So that was the question. I'm gonna let you guys think about it a little bit, and I'm gonna finish the rest of this program, and then when I get back, I can read the text channel to see if you guys have the correct answer. Alright, so there we go. The answer is, okay, you guys are all correct, but nobody really nailed the answer. They wanted to write Unix. That's what they wanted to do, was to write Unix. They were trying to write an entire operating system. At first, using only assembly language. That's why they wrote the C programming language, so that they don't have to specify all the low-level details and they don't have to track everything by hand, because now they can rely on the C compiler to translate some of the high-level constructs into assembly language. That was the idea. All right, so Marco is correct. So I would be more specific about what quote-unquote current address is referring to. So the current address is referring to the address of the LDI instruction. And otherwise, Marco is 100% correct. It's just that the term current address is not very specific. I just want to be very, very specific in this case. The dot is basically representing the address of the instruction of that line. There we go. All right. So I just got the program finished. Line 51 puts the offset of X to register B. Line 52 adds the stack pointer to the offset. So now we have the address of X, in register B. And then line 53 is storing the return value, which is in register A by convention, of get I into B, where B is pointing to in memory, and B is already pointing to the local variable X. So that should store the return value into X, and that should finish the entire program. Cool. So now I think we are ready to test run the program. So let's go ahead and do that. So we have a cat struct.ttpsm, pipe it to xclip-cell clip, and then we go to the assembler. I was using it just a little bit earlier today because I was trying to. We'll get to it. I'm looking at the time. Yeah, I think we can get to it. Okay, so get rid of that column, and then we paste the program in. Make sure that it doesn't complain about anything. Okay, so it's looking good. Go to RAM file. So everything looks good. And then we download the CSV. And we'll put it into struct.csv. And then we go back to, oops, wrong one. We go back to the command line interface, and then we just go back up to the command to run it, right? So we do a dash load of struct.csv this time. Oh, you guys cannot see the end of the terminal. Let me move it so that you can see the entire thing. There we go. So we redirect the output to struct dot what was it again? TSV. There we go. And then press the enter key. Okay, did not get stuck in the infinite loop. And I know some of you are thinking, okay, what if I got stuck in the infinite loop in the homework? How do we deal with that? Okay, so I made a video to address that specifically today, and I posted that into the text channel of the 20th. So if you have watched that already, then you already know the answer. But we'll get to that point. Okay, I'll get to a program that will illustrate several things at the same time. So now we can go to the trace analyzer and then go to sheet 1. So don't forget to get to sheet 1 first before you import. And then the import user interface has changed a little bit. So after we upload, okay, come on. And the program we want to upload is struct.tsv, which is right here. All right, so the import interface has changed just a little bit. They made it a little bit cleaner. So now you have to specify, replace current sheet in a drop-down box instead of using the radio button. And then the separator type is exactly the same thing. It used to be a radio button, and now it's a drop-down box. Just select tab. And then uncheck convert text to number, dates, and formulas. So otherwise, it's the same thing. You just have to kind of, instead of using the radio buttons, now you have to use the drop-down box to do the same thing. Cool. And this one should be a fairly short program, so it shouldn't take much time to finish the analysis, and it shouldn't be a whole lot of numbers of lines either. So the first thing I go is to go to the summary. This one takes 179 rows. So we go to analysis. So now it's important to understand what we should be seeing, right? Because if you want to know whether the program worked or not, you kind of need to know what does it mean when the program worked? What should I be expecting if the program is indeed working? So if the program is working, we should see 15 stored in X. Okay, that's the first thing. But we should also see 15 stored in member I of var. Okay, so those are the two things that I should be looking for. So now the question is, but where is X and where is member I of var? So now it's it's important to go back to the C code, because the C code kind of tells us where those things are supposed to be, not in C, but in terms of the order of how things are defined. And obviously, I have just lost track of my online GDB window. So there we go. This is a really handy feature, by the way. Having tab search, is really, really helpful. When you're like me, when you have like close to 100 tabs open across all, several, like 7 or 8 windows, it's really helpful to have this feature just to quickly locate a particular tab by its name. All right, so getting back to here. So var is going to take up the first 2 bytes, right? So member I of var is going to be we have 3 bytes total of local variables. So this is going to be f. Okay, it's difficult to count backwards when you start with ff and you have to count backwards twice. So ff is going to be x, and then fe is going to be var.j, and that makes fd to be var.i. So var.i is fd, var.j is fe, and then x is ff in memory. There we go. Okay, so now we go to the trace analyzer, and then we check that. So the trace analyzer is at the earlier part, which is here. All right, so now we look for RAM write operations. Okay. Oh, okay, too quickly. There we go. There we go. There we go. This is okay. We have to go back a little bit more. There we go. So that's the first write operation to RAM. This is where we initialize var.i with 15, which is at location fd. So that's good. We just confirmed that we store 15 into var.i. And then we have a whole bunch of stack write operations to pass the argument, and then we push the return address, and then we accessed that location and then return the value. So now we can see how x, which is at location ff, is getting the same value. We also confirmed that the stack pointer goes back to 0, and 3-1 should correspond to the address of the halt instruction, and that's easy to check, because all you have to do is to go back to the assembler and then go to the assemble tab, locate the halt instruction, and just make sure the hexadecimal version of that address matches the last entry in the trace in column A in the analysis tab. So everything is good. There we go. All right. So this program, between the C code, the TTP ASM assembly language code, and the trace. Okay, so between those 3, if you really track things down like one by one and not try to skip things, you should be able to document the source code, the TTP ASM source code, so that you can You can verify what is in which register at any particular time, at any particular moment of time during the execution of this program. And that will be an exercise for you to do. Now, if you suspect that you might make a mistake and you don't want to kind of get a wrong understanding of the program, next Tuesday, you can ask me for the documented version. So I can give you the commented version, but I don't want to give it today so that you have a chance to work on it first. But if you're not sure whether your understanding and your comments are correct or not, you can ask me to give you the quote-unquote answer next Tuesday, because that's fine. Okay, but I do want you to spend some time to work on this yourself first. Cool. All right. So the next thing we're gonna do, we have. I'm just looking at the time. We have about 15 minutes, I think. Yeah, so we got 15 minutes. So we're going to work on a second sample program that makes use of structures. And this time we are going to have a member inside the structure, just like this one, except that member is going to be a pointer, pointing to a structure of the same type that we are defining. Okay, so the description is difficult to say. It's better off to just to give you the code. So we'll go ahead and, okay, obviously I need to find my online GDB window. See how useful it is? Really cool. Alright, so I'm just going to modify this program a little bit. Maybe I should copy and paste it first. So I'm going to copy and paste this so that after the class I can give you the source code of this. There we go, and then we control D. Okay, so now the program is backed up on my local computer, and I can just go ahead and modify this one. So I am going to modify it so that it looks like this. Alright, so let's not worry about the rest of the program yet, okay? Let's just focus on line 3 to line 7. And most of all, we look at line 6 and go like, what is going on here? Is that even legit? I mean, can we refer to Struct C when we are inside the definition of Struct C? Strictly speaking, you cannot, but that's not what I'm doing. P itself is not a Struct C. It is just a pointer to a Struct C, and that is perfectly okay. So inside a Struct C definition, you cannot have a member that is a Struct C. That is strictly, doesn't make any sense, okay? But you can certainly have a pointer to a Struct C, okay? So this is, okay, if you want to understand this, okay, you can basically think about a Struct C as a house. And then you think about Struct C asterisk on line 6 as the address of a house. So the question is, can you have a piece of paper in a house that contains the address of a house? Absolutely, right? I mean, whenever you use an envelope, okay, you are writing down the address of usually a house on a piece of paper. Now, obviously, this analogy is not going to work in a few more years, because people go like, what? What are you talking about? What is paper? What is an envelope? And by the way, what is writing? I don't understand these words. Okay, I'll show you a picture from the year 2000, about people actually using paper and pen and writing on stuff. Yeah. Yeah, that day is going to come. Unfortunately, that day is going to come when I'm still alive, where people would ask me, what do you mean by writing? What do you mean by paper? We don't understand that. Yep. Well, that's the pace of technology right there. Yep. All right. So now, we are gonna change. I mean, the subroutine get I can stay here. It doesn't really matter. But what we want to do is to say, let's do something like this. Okay. So this time I'm not concerned about member I, which is really just an integer that I store into the structure. I want to play with member P this time. Okay, and I'm gonna say, let's do it like this. In other words, I'm just saying, let's write on an envelope the address of the house where the envelope is in. Well, is that legitimate? perfectly, right? I mean, just think about, okay, think about where you're at right now, okay? Hopefully you're at a certain place where there's an address, okay, in a house or building of some kind, and you just pick up a piece of paper, and then you say, I'm just going to write down the address of where I am right now on that piece of paper. Well, what's the problem, right? I mean, there's no problem with doing that whatsoever. So if there's no problem with writing down the address of the house that you're in right now on a piece of paper, then why would line 19 be a problem? Because it's exactly the same thing. You're taking the address of a structure so that you can update a particular member of that structure to store that very same address. There's no problem with doing this. Okay, so remember the analogy. Okay, next time you look at line 19, go like, no, no, we cannot do this. Yes, we can. Not a problem. All right, so now I want to make a loop out of this. Okay, so let's just say that we want to keep looping, and this time we need a pointer too. So we need to declare a pointer up here. So we have struct c asterisk p as a pointer, and then someone is going to say, but Jack, you have the same thing on line 6. Are we going to have a problem? The answer is no, we are not going to have a problem, because line 18 is defining a local variable p, and then on line 6 it is defining a member p inside a struct c. So these two p's are unrelated, completely unrelated, and the compiler would not have a problem with this. Alright, so next we have p equals to the address of var. There we go. And then in the loop here, we are basically just saying as long as p is not null, and we're going to do something like this, p equals to whatever p is, the member p of the structure that p is pointing to. Okay. Are we good with this one? Are we good with line 24? Okay, we got Darvish is typing. So as Darvish is typing, I'm going to start to work on the C version of this code. So I'm just going to copy struct.ttpasm to I'm just going to call this ptr.ttpasm. All right, and then we'll work on that code. Okay, so this is going to be a modification of the other one. So I'm going to keep the program just mostly the same as the other one, just change a few things. All right, so we got some questions. Yes, this is an infinite loop. It's not going to get out, because when we chase the pointer p, it's always going to go back to itself. So yes, so Darvish, you are 100% correct that this is going to be an infinite loop, because I wanted to show you guys how to debug a program when you get into an infinite loop. So that's the idea. Okay, so very good observation. But we are not going to have a new frame, because there's no calling. I mean, line 22 all the way up to line 25 in the C code is not recursive. It is really just, a run-of-the-mill loop, just going around and around, but it's not going to take up any more stack space as it executes. It doesn't even call anything. I mean, it's not really even calling anything. So it shouldn't be a problem. Okay, so we do have a minor problem here, because getI uses p as the name of the parameter. That's going to interfere with p as a local variable in main. So we can do one of two things. We can go to main and change that p to a q. Okay, I mean, this is a problem of the assembler not having the concept of a scope. So so that's kind of the issue. So we're just going to change all the references to p to q in this case. All right, fine. I'm going to have to use the gear and say do not autocomplete. There we go. Basically, I'm telling the editor, I know what I'm doing. Don't fix it. All right, so we have, oh, okay. Apparently not entirely. Alright, so can we undo? Yes. Okay, very good. Okay, replace that with Q. I wonder if the editor has a tool. I cannot remember the term for that sort of thing, but I wonder whether it has a tool that will let me just going to change the name of a variable and just propagate that change automatically to all the references to that variable. Refactoring, that's it, that's the term. Refactoring, there we go. Okay, so now we can go back to the assembly code, and hopefully we have time to finish this because this is going to be a fun one. Alright, so okay, let me just change a few things. We don't really want X anymore. It is not useful, so get rid of X because there's no need for this anymore. Okay, so we are just focusing on Q this time. Oh, one more thing, because we do want to run this program in the debugger just to make sure that we are going to be stuck in a loop, infinite loop. So we click on debug, and then we run the code. Yay, we are stuck in an infinite loop. Okay, very good. Alright, so now we can go back to the assembly code because we just want to finish the implementation. So P is taking the place of X, okay, oh, sorry, Q is taking the place of X. There we go, and then we fix this. And we are not initializing, oh, we are initializing Q. So we are just changing a few things here. So instead of computing, right, so we are computing the address of Q, P, sorry, member P. Okay, that is still P. And then we are going to store the address of var in it. So this portion does have to change. So we have an LDIB var add AD BD, sorry. Then B becomes the address of var, and then we are going to store that into member P of the structure that we know as var. Okay, so there we go. I'm just staring at the code, double checking everything in here. So they're all good. Okay. So that is line 19. And then on line 20, we have to initialize local variable q with the address of var. Alright, so let's get rid of this call code here. Alright, so we are not calling. We're not going to store anything back. So now we just so now we're implementing the code on line 20. We are computing the address of var. Okay, so something that we have done already is already in register B. So we could have just let's just keep it in register B. So now we're only focusing on computing the address of Q. So we have LDI A with Q add AD, and then ST A B. In other words, register B had the address of var from before, and I'm keeping it. So we are just storing the same thing, which is the address of var into local variable q this time. And now we are ready to implement the loop. And so we have while begin, while end, and then at the right before the end, we want a JMPI back to the beginning part of the while loop. Okay, so that's a typical way to write a loop. And then now we specify the condition and when we can get out of the loop. So the condition is to get to the value of q first. So LDI AQ add AD LD AA. So now we have the value of q loaded into register A, and it's time to use AND AA to kind of force it through the ALU so it can influence or it can update the Z flag accordingly. And if it is indeed 0, we are getting out. So that means we're getting to while end as a label. Otherwise, we perform what is equivalent to line 23 in the C code. Alright, so what we're doing on line 23, well, we need to get to member P of the structure that Q is pointing to. So how do we do that? You cannot, you have to start with Q. So we're going to do LDI A with Q, add AD. So now we have the address of Q in register A, and then we are going to dereference it. Okay, so we need a LDAA. So we first have to dereference register A so that we can get to the value of Q. Once we get to the value of Q, which is a pointer, now we can load another register, say B, with the offset to member P from the beginning of a struct C. So that will be C underscore P, and then we add register B to register A, and that will complete the right hand. Oh wait, no, one more time. Okay, we need another LD, because what we have done is to compute the address of member P of the structure that Q is pointing to, but we don't want the address of that member. We want the value of that member. So we have to use another LDAA to get to the value of member P in the structure that Q is pointing to. Alright, so now we can get to the left-hand side of the assignment, which is just Q. So that is pretty easy to do. LDIB with Q, and add BD. So now B has the address of Q as a local variable, and we just need to store. Okay, so we store to where B is pointing to, the value of A, and that should be it. Okay, so let's check it. Yes, we are running out of time, but I think we can just do this in another 5 minutes, unless I make a stupid mistake somewhere. And then we go to the assembler. Alright, and then wait until we get the result from the assembler. I think everything is good. Yep. And then we get the CSV download as ptr.csv. And then we go back to the command line. Alright, so I suspect this is going to be an infinite loop. I hope it's going to be an infinite loop. So we'll go ahead and run it so that I can show you what it's going to do as a program that has an infinite loop in it. Okay, there we go. We direct to ptr.tsv. Press the enter key. This is good news. It looks like it's going to be an infinite loop. So you might think, now for those of you who didn't watch my video earlier, you might think, oh no, my program is not coming back. This is all bad. Well, nope. You just have to type Control-C on the keyboard to stop Logisim, from going any further. Okay, but depending on how long you wait before you press Control-C, you might end up with a gigantic TSV file. Like in this case, I end up with 42,571 lines. And that is really long. And because it's kind of a tight loop, so there's a lot of repetition in it, I didn't have to wait this long. So if you're using Linux, you are in luck, okay? Because if you're using Linux, you can repeat the same command and just precede the entire command with timeout, and then you can specify how much time you want Logisim to run before it is stopped. Okay, so if I just wanted to run for 2 seconds, you just specify timeout in 2 seconds, and then the command itself, press the enter key, wait for 2 seconds, and it automatically terminates. It's like, oh, this is really, really nice, right? I have already looked into Windows to see if CMD has a equivalent command, and the answer is no. So it's not too bad. You just have to time it yourself. You just have to press the enter key to run the command, and then just have to count 1,000, 2,000. Control-C, stop it. That's all. I mean, you lose a little bit of convenience, but it's not a deal killer. All right, so now we get back here, go to sheet 1, and then we say file, import, upload, and this one it is ptr.tsv. Double click, and we want to specify replace current sheet, tab as a separator, and then uncheck convert text to numbers, dates, and formulas. Click import data. And then wait for the progress bar to finish. The summary should be done already because summary is really just counting the number of rows that are non-empty. So we have 2,883 rows that are non-empty. But if you want to find the loop, it's easier just to go to the bottom. Just go to 2,800 something. Because the loop is still ongoing, remember. So we are basically, interrupting the loop itself. So if you go straight all the way to the end of the whole thing, there has got to be a way to go to a specific row. Okay, let me check. Edit. Nope, definitely not from here. So maybe there's another way to get to a specific row. Or we can ask Omar to write a macro for us. And then, then we can use it. Control F. Control F finds something. Can you use it to go to a specific row? No. Unless I miss something. Alright, so let's keep going, keep going, keep going. Alright, so we are now at the end of the trace. And the type loop is somewhere in here. So now the question is, how do you identify the beginning of the loop and the end of the loop? So we can see 25, location 25 is here. So we just have to find the previous time location 25 was visited or executed. So we just have to scroll back until we see 25 again. And you can see these are pretty sequential because we are not calling anything. So the last time we see 25 is here. But you can also see that the infinite loop actually starts with location 23. I shouldn't say 23. It's actually 23 in hexadecimal. So that gives us a pretty good clue that 23 in hexadecimal is the beginning of the type loop that we are stuck in. And the last location of the loop is location 35. So between 36. So between 23 and 36 is the scope of the type loop that we got stuck in. So if you go back to the assembler and go to the assemble tab, now you can go to look at the addresses, right? So we go to location 23, which is here, and then we go to location 36, which is down here. That is where the loop is. So if I want to highlight it in the spreadsheet, this is the scope of the type loop because it starts with location 23, it ends with location 36, and we just got stuck in here. So typically, if you are stuck in the loop, that means whatever code is supposed to get you out of the loop, which is line 67 here, did not execute. And in order for the JCI to not to execute, it means the Z flag was never set. If the Z flag is never set because of the AND AA instruction, that means the register A is never null, which also means Q as a local variable was never null. So that would give you some idea of where the logic might have gone wrong in order to get stuck in a loop. Alright, so I'm getting back to the text channel. Top left of the fx function cell may allow you to jump to cells. Okay, so we are talking about here. It allows me to go to ranges. Let me go back to the trace analyzer and see if it looks different. I think I can just type over this. Maybe that's how I can get to a specific row. Nope. Okay. I'll look into it. Yes, I did go over this in the video, except in the video that I pre-recorded earlier, I did not use a structure that points to itself. So we basically we are chasing our own tail using a pointer as a member inside a structure. Okay, okay, so I'll try that. 1000, 1000. Yay! Okay, that works. Okay, so now we got a way to go to a specific row. Thank you. All right, well, that's going to be the end of today's lecture. Oh, by the way, we have a new lab because every single time I make a lab due in a week, somebody is going to ask me, so does that mean we don't have a lab tonight? We do have a lab. This is going to be an easy one, okay? Trust me, this is going to be an easy one because we talked about all of those concepts in today's class. Okay, so this is just really just for reinforcing the concepts that we have already talked about. The passcode is the access code is just struct itself. So Aaron has got the right access code to the lab at the very beginning of today's lecture. Good job. There we go. And I'll pin it. Okay, well, that's fine. Not a problem. I mean, if you guys can get to the access code early, getting started early is not a bad thing. All right, so that's that. I'm going to go away for about 10 minutes, then I'll be coming back to answer questions. Doctor Who, that's it. Doctor Who. Think of how boring life would be when someone is all powerful. There's no challenge in life anymore. That would be bad. Okay, so here's a question for those of you who like to deal with logic. Would an all-powerful creature be able to kill itself, himself, herself, themselves? That's a question, okay? So I'll let you ponder on that as I go get something to eat. I'll be back in 10 minutes. So I'm gonna stop all the streaming.